Okay, here we go. So new topic today, derivatives. It's a little bit weird. Here we are in the fourth week, at the end of the fourth week of the class, called Multivariable Calculus, and we're just finally getting around to actually doing a little bit of multivariable calculus. Right? Seems a little bit weird. Of course, there's a lot of setup work to do. We need to understand multivariable functions, various tools that we're going to be doing a lot with, lines and planes, cross products, dot products, all the stuff we've been doing. The first thing I want to say about derivatives, multivariable derivatives, is that there's lots of kinds of them. All right, so this is new. This is different from single variable calculus. In single variable calculus, there's the derivative. And that's it. Right? So that is not the case in multivariable calculus. There are many different multivariable derivatives, and they're interpreted in different ways. The interpretations of them are connected in ways that are not terribly surprising, but they are in fact different. So anyway, make sure not to just hang your hat on one kind of derivative and one way of thinking about it, because it's not good enough. We need to be able to understand derivatives, each of several different kinds of derivatives in each of several different kinds of contexts. Right? So long discussion. There's a lot to say about derivatives as we go through this chapter. Okay, there is one thing that they all have in common. I call the unifying idea here, and that is they relate input changes to output changes. If you have a function, keep in mind a function is a thing where something goes in and something comes out. Well, no surprise, if whatever goes in, if you change that input a little bit, it's going to change the output in some way. So all of the derivatives that we're going to talk about in this class will in some way, in their own unique, different ways, relate input changes to output changes. When you tweak the input a little bit, how does that tweak the output correspondingly? Okay, so you'll look for that unifying idea as we go through this. So we're going to start with partial derivatives. Most books start with partial derivatives. We're going to start with partial derivatives for three reasons. One, they're easily relatable. You're going to see that momentarily. They kind of feel a lot like single variable derivatives, so that's not a big stretch. It's very satisfying in that way. And secondly, they're super easy to compute. Everybody likes that. Right? So the third reason, which I didn't write down, is that we are starting with partial derivatives, also in part because our book starts with partial derivatives, and it makes things complicated when you do topics in an importantly different order than the book does. But let the record show, my own calculus book does not start with partial derivatives. So I want to give you a warning here. Don't think that just because we're starting with partial derivatives that somehow these are the fundamental, cornerstone way that you should think about multivariable derivatives. I don't think that's true. Yeah, go ahead.
Is there any function that
Yeah, I think there is, and we'll talk about it a little bit later on. It's going to take us a while to get there, but it's one of these things where it's really hard to start with the right answer. It's really easy to motivate a first shot, have some aspects of it that are cool, but then you realize the shortcomings, and then you try something else, and you bang around, and you experiment, and you get lucky, and then eventually you realize, oh, here's really the way to think about it. So we're going to build up to it over time. Right. So, again, I'm starting with partial derivatives for a variety of reasons, but don't just, don't orient all of your understanding of derivatives around this one concept. I don't think this is the right concept to do that with. My opinion. Everybody's different. Okay. So here's the definition. Note here we have a multivariable function. Multivariable because there are aka multiple input variables. Right? Now, importantly, multivariable refers to the number of input variables. The number of output variables is surprisingly not that interesting when it comes to taking derivatives. What it means to take a derivative, how that's going to look, how we're going to interpret it. Dealing with multiple outputs is a lot easier than dealing with multiple inputs. So, in fact, y'all have already seen an example of that, right? We took derivatives of parametric curves. A parametric curve, a parametrization is a function with multiple outputs. And how did we take the derivative? We used the exact same formula we did in single variable calculus and got a familiar interpretation about velocities. So, not that big a deal. Here's where it gets different. What if you have multiple input variables? All right, so our first step in that direction, we got all these input variables in different input variables there. And the idea is we're going to hold all of them constant except for one. So I'm going to use gray to indicate that which I am not allowed to change here. All right, so that's staying the same. Not allowed to change. For the purposes of this definition, those gray things don't move. All that's left to change, all that's left that is any more allowed to change is this ith input variable. And so what have we got? We've got a function where I'm not allowed to change these other variables. I'm only allowed to put in one number. That's a single variable function. All right, so it's a kind of silly observation. You might even call it a cop-out, right? That we have a multivariable function. Okay, how about step one? Let's turn it into a single variable function by decree, right? And then now that we have a single variable function, we take the plain old Math 111L derivative. Notice that we put in x plus h and then subtract the value when we put in x. Subtract, divide by h, take a limit. It's good old single variable derivative of that resulting single variable function. Okay. So this is called a partial derivative. All right, and like I say, it seems like a cop-out. How unnatural. Let's just pretend all this stuff here is fixed. How's that ever the case in the real world? These are all reasonable gripes. Okay, so here we go with a little bit of notation. Y'all recall the Liveness notation for single variable derivatives. That's not quite what this is. It's motivated by the Liveness notation. But we use this slightly different symbol here. That slightly different symbol, not a delta. Please be sure to note that. It's not the lowercase Greek letter delta. It's a symbol that, to my knowledge, was made up for this purpose with the intention that it should look like a D, kind of. Because this is kind of sort of a single variable derivative, and so, we want it to look familiar. But very importantly, not a D. Because this is not actually a single variable derivative. Somebody did not come to me and say, here's a single variable function, take the derivative of it. F, this guy here, is not, at the start of this conversation, this single variable function, it's not a single variable function. Look at that. Clearly a multivariable function. So I can't just say df, dxi, that would be an abuse of notation. So this little symbol here, this little what we call the partial symbol, is our way of saying, look, it's kind of, come on, it's the same sort of thing. It's, okay, a little bit different. We have to sort of cheat to make it a single variable function, but with that understanding, then we're going to basically do the single variable derivative. Okay. So please do be careful with this. If you were to write alternatively df dxi, that's wrong. Okay, so this is not an sort of I choose to do it the other way. You have to use this notation. Yeah.
Does it have a name?
I'm sorry?
Does it have a name?
I've always just called it the partial symbol, and I've never heard anyone call it anything else. So yeah, let's just go with that. Okay. Backwards 6. Okay. Right. Okay. So how do we compute partial derivatives? Now, we've written down a formula that looks like the concept for which we have all these shortcut rules, but it's not the same concept, and it's not immediately obvious that you can just use all those shortcut rules. But the good news is you can, because if you think about what we're actually doing here, we are literally taking a single variable derivative. Because after we view it as a single variable function, we in fact do have a single variable function, and it is the single variable derivative that we're actually computing. So you can use all of those old rules. And so here's our first example. This looks like a really hard problem. I'm going to take the partial derivative with respect to y of this monster. Yikes. Right? Feels like, my gosh, I have to use the product rule twice. Cotangent of this junk in here, I'm going to have to use the chain rule, so it seems. But, in fact, you don't. If you look at this function, keep in mind the very first thing that we're going to do is we're going to consider all the variables other than y, everything else, constant. Right? That means that e to the x is a constant, and cotangent of whatever that is, that's all there's no y's in there, so that's all constant. Right? All of that's constant. So what we really have here is we're taking the, after we've decided to hold all this constant, we've got a constant times y squared. That's what this function is, constant times y squared. That's an easy derivative to take with respect to y. As for, what's not a constant, we're taking the derivative of y squared, and we get 2y. And the constants just stick along for the ride just like they do in single variable calculus. Everybody happy? Everybody see how that was easy? Okay. So I nominate partial derivatives as being the easiest derivatives to compute as a general rule of the many different types of derivatives that we are going to have seen by the end of this course. And I mean even easier than single variable derivatives. Because in single variable derivatives, you don't get to say, oh, yeah, you know what? I choose to view all this stuff here as constant. Wouldn't that be nice? Can you imagine a single variable calculus class and you just get to say, oh, this great big nasty function here, let's just pretend all this stuff is not there. Right? You don't get that luxury, and you do when you're taking partial derivatives. So now you have to make the right choice. You have to choose as constant the things that aren't the variable you're taking the partial with respect to. So it's a restrict, but nevertheless, it's always convenient. Yes.
When you say choose one that works well, would it not be the case that what we're interested in? When you say choose one that works well in terms of what will end up fixed and constant.
Oh, I didn't mean to say choose one that works well. The question's been posed to us, partial derivative with respect to y. Right. So we don't get to choose what we're taking the partial with respect to. That was given. That was part of the question. And I'm just saying that given that we are taking the partial derivative with respect to y, then that's the only stuff that I have to view as being real, and that I can then, as part of the definition, I get to choose. Maybe choose is the wrong word. It's not like I can choose to view x equal to y or something like that. I have to pretend like all that stuff is constant.
So what you're interested in knowing about a particular function would motivate which derivative you want to take. Oh,
sure. Yeah, and we'll talk about what these things mean and how you might make such choices in a couple minutes. Yep. Okay, so a couple quick examples. How do you take this partial derivative? Partial with respect to x of that business. And this looks hard because you see a function raised to the power of another function. And looking at a function to the power of another function, y'all might have memories of logarithmic differentiation. Y'all remember that one? Okay. And it's, there's steps and the product rule and logs, obviously, and it's kind of annoying. It's doable, but it's annoying. But not here. Here, because x is the variable we're taking the partial with respect to, here we have a function to the power of a constant. And we take the derivative of this with the good old power rule. First thing everybody learned in single variable calculus. And it, goes down to the front. You subtract 1 from the exponent. And then once you work the chain rule into it, then don't forget to take the derivative of the inside, thus giving you the 2x. Okay, so you're going to get the willies the first time you do that because I die with if there's a function in the exponent, I thought we weren't allowed to do that, and this is a function. this exponent is a function, right up until the point where you say, I'd like to take the partial with respect to x, at which point it's now a constant. Okay, so like I said, you get the willies, but it's actually fine. Same sort of deal, function to the power of a function. In this case, we're taking the partial with respect to z, and the base is a constant. And so we all remember the rule for taking derivatives of exponentials. And this is an exponential because I have a constant, right? All constant to the power of z. It's like this is a to the z, where a is a constant, because that is a constant. Okay. Sometimes, maybe not quite so lucky. So here, let's see, you're taking the partial with respect to y. So there's a y and there's a y. So when you break this down as a product, well, yeah, neither one of the factors in this product is actually a full-on constant. Here I have a function of y that's maybe not as function-y as it looked at a glance, and likewise here, right? Because I do get to pretend like x is a constant, and that's nice. But it is still a function times a function, so you have to use the product rule, think things through. But still relatively easy. Okay, so what do we have so far with partial derivatives? We have an algebraic definition motivated by, well, this worked last time. Fingers crossed. Seems like it might be, who knows, maybe this will actually mean something. That's not a very good motivation. But anyway, we're trying this for lack of better ideas. So we have a definition. We have a notation. And we've cranked it out on a few occasions. But what can we do with this right now? I've made up a rule for how to manipulate symbols around. So what? Right? This doesn't do anything until I can explain what this means geometrically. How is this natural? Right? Until then, I'm just kind of writing stuff down. Y'all remember the deal with, when I was like 5 or whatever, and I figured out a much better way to multiply numbers, and it was real easy to do, and you just concatenate, and why are we not doing this? The world's going to be a much better place. No natural interpretation, no uses. Okay, so what is the geometric interpretation? Well, several answers to this question. How you interpret calculus in a geometric context depends on the geometric context. Right? So now recall, recently we've spent a bunch of time, I made a big deal out of how a graph is a very, very different construction from a level set, which is not to be confused with when you parameterize a curve or something like that. So these are 3 different connections between algebra and geometry. And the pictures, how the pictures relate to the functions, all different. And I made the assertion that the calculus is going to look different in all these pictures. So here we are. Now we know one item of calculus, partial derivatives. I'm going to show you how do you make sense out of them in the graph context, and then I'm going to have a different geometric interpretation for how do you make sense out of this in a level set context. Okay, so starting with graphs. The good news, we already have all the tools that we need. We already have existing geometric interpretations of everything in this process of taking a, let's say, arbitrarily a partial with respect to y. So here's the rule. Now, by the way, notice we have a function from R2 to R1. So this is a function of x and y. Graph means we're going to take that function of x and y and set it equal to a new variable, z. And that new variable z is one axis. The input variables x and y are the other axes, and you draw the graph. We have that whole process that we talked about. Okay. So here's the equation for this graph. We know we're going to get a surface. So what are the steps when you take a partial derivative? Well, keep in mind the first step in taking a y partial is you fix all the other variables, not allowed to change, right? So there it is. Fixing x, setting x equal to a constant. Looking at this picture, what would it mean to say x equals a constant? And x equals a constant is a plane. It's a plane in this world. where, let's see if I can draw this decently well. It's a plane where, it's sort of like this. I'm just trying to connect the pictures to each other. It's a vertical plane perpendicular to the x-axis. Okay, so, all right, well, again, looking back at the definition of a partial derivative, set all the other variables equal to a constant. Okay, fine. We're taking a partial with respect to y. We set x equal to a constant. Geometrically, that looks like this. We already knew that. Okay. Next thing we do is we take the derivative with respect to y of the resulting single variable function. Well, here's the thing. The resulting single variable function, what is that resulting single variable function? We've got this green graph in the first place, and we're taking a cross section with this gray plane. That cross section is a curve. And it's not hard to persuade yourself that that curve is the graph of the single variable function we're now taking the derivative of. So, derivative with respect to y says, well, look, you can see it right here, z is a function of y. Or maybe it's offset a little bit. Maybe we do it like this. Z is a function of y. Right? And derivative means look at the tangent line and compute the slope. So it means this. All right, so here we go. Here's our interpretation of the partial derivative with respect to y. It says, I'm going to look at this curve. That's tangent to the graph of, I'm going to look at this curve that is the cross section of the graph of f in the y direction, and the partial derivative is the slope of that tangent line, like that. As you go in the y direction. How are we doing? Everybody happy with this interpretation? All right, so that's geometrically natural. I mean, in the context of graph, we look at graphs all the time. We like graphs. Y'all probably like graphs more than I do. And in this context, slope of a tangent line, it's not only geometrically natural, it's also familiar. And this is it's a little different. With single variable derivatives, it's the slope of the tangent line, end of story. There is only one tangent line. Here, okay, sure, our surface, it starts off. Well, there's lots of different directions in which you can take cross sections, and we're picking one arbitrarily. We're picking that. We're going to look at a cross section in that y direction, and look at the tangent line in that direction. So there's something a little different about it, but it's very familiar as a concept. Okay, now here's an exercise I want you all to do on your own. I want you to think this through for yourself. Persuade yourself that when you take the x partial, then we're going to be looking at the slope of the tangent line the slope of the tangent line to that cross section of the original graph. All right, so think it through. It's very analogous to what we just talked about. I want you all to think through those details. Okay, now, again, that was one point of view on partial derivative. That was, if you have the good fortune of looking at a graph, which you will not always. Right? So what if we're in this circumstance here, and I like to start with this point of view. This is not a level set. This is just, suppose you're just looking at the domain, and the target, the function f is like this. The function takes the domain, points in the domain, and gives you points in the target. So, if you have this domain point of view, what does the partial derivative do in this context? Well, the partial derivative is still a single variable derivative ultimately. I mean, you do have to, let's see here, we're taking the partial with respect to y, so we're only moving y. Y is the only thing allowed to change. X, X is fixed. Z is fixed. Those are not allowed to change. And so with X and Z fixed, you can see there's only one way left to go. We have to go in the Y direction. And as you go in that Y direction, the partial derivative says how fast is the output changing. So the partial derivative is the relationship between this yellow input change in the domain and this purple output change in the target. What's the relationship between input changes and output changes? Which, of course, by the way, I mean, hopefully you recognize this idea of relationship between input changes and output changes. That's what a single variable derivative is too, right? Single variable derivatives. It's the proportion between input changes and output changes. Okay. What about in a level set context? So, level sets, you'll recall. Let's see here. Level sets. Recall are curved, and I'm drawing a particular case of level sets. Oh, man, I missed. Particular case of level sets there. So this first purple line is the level set where, f equals some value, some fixed value. The next one over is a different curve where f equals a different constant value. And, again, you might think of this as a hiking situation. The purple lines represent contour lines, like level. That's the name, level curves. Okay, so with that metaphor in mind of altitude, I mean, just use your geometric intuition. If you're going that way, right, taking a partial with respect to x, x is the only thing allowed to change, y is fixed. And notice this green arrow I've drawn here, y is not changing. We're going only exclusively exactly in the x direction. What's our experience as we climb this mountain? Well, it's a rough experience. I'm going almost straight up the cliff. That's hard, right? I mean, in that short of a distance, like an inch and a half of distance, I'm climbing 2 full contour lines. My gosh, what's that, 200 feet over that short little distance? That's real steep. Right? So, the x partial is large, as I've got these contour lines drawn. Okay. On the other hand, now suppose that I'm going in the y direction. Well, that partial derivative is small because, well, look, I mean, as I go in that direction, I'm not going exactly along a contour line over which the function is not changing at all, but I'm moving almost tracking the contour lines. I'm going slightly uphill, I suppose, but nowhere near as much as there. Right, so here, there's much less change. So the y partial, as you're moving in the y direction, lower output changes per unit input change. So note that this is a different geometric interpretation. It would be massively, tragically wrong to say that the partial of f with respect to x is, it's a slope. What is a slope? Slope of, the curve. Here's a curve. It's probably the slope of that curve. No. Absolutely false. Everybody see why that's completely wrong? So if you try to take a graph context interpretation when you're actually looking at level sets, you just get completely invalid interpretations of what you're looking at. So this is I guess my first example then of why it's so important to make sure that you keep ever present in your mind, wait a minute, what's my context? What kind of a picture am I looking at here? There's a picture. What is that picture? What has that got to do with this function f that I'm looking at, whose partial derivative I'm computing? And so make sure you're very, very clear at any picture you're looking at. Am I looking at level sets? in which case how close the contour lines are together. The closer the contour lines are together, the steeper it is, and so the larger the partial derivative is. Or am I in a graph context, in which case the partial derivative is, well, it's the slope of the graph. End of story. Okay, let's talk about tangent planes. We'll get to the tangent planes in a moment. First, I want to talk about linear approximations. And I know y'all remember linear approximations. Here's the formula for the linear approximation to a single variable function. There's different ways you can think about it. I want to start off with an algebraic point of view on linear approximations. Here's my favorite way to think about how to motivate a linear approximation. And that is that this linear approximation is a function that mimics the original function. Okay, so we've got this original function f. We've got this new function L. I've written down a formula for it. Note that, of course, L makes reference to f. It makes reference to the value of f at this point A. It makes reference to the derivative of f at that point A. But they're different functions. I don't even know what the formula for f is. I have a formula for f. Okay, so what's the connection between these two things? Again, this is my favorite point of view on linear approximations. Linear approximations are functions that mimic your original function in value and in derivative. So this linear approximation has the feature that it's got the same value as f at the point A, and it's got the same derivative as f at the point A. If you're at the point A, it's pretty hard to tell the difference between f and L. They've got the same value at the point A where you currently are. They've got the same derivative. They've got a lot in common. Everybody see what I'm talking about? Just mimicking. Okay, now note this is algebra. F is a function. That's an algebraic object. L is a function. It's an algebraic object. Okay. Those are algebraic things. Now let's think about how I would visualize these things geometrically. And I'm going to draw their graphs. No surprise. This function f, its graph, see, graph, setting a new variable y equal to the value of that function f. Its graph is some curve. Our function L, its graph, again, graph, because I'm setting the values of L equal to that new variable. Its graph is a line. And it's not hard to argue that if this L function is mimicking the f function, but it's doing its best impersonation of f that it can possibly do at that point, you've got the same value, you've got the same slope. Not surprising, it's a tangent line. Right? Okay, so the graph of a linear approximation is a tangent line. The linear approximation itself is a function. So I do think it's very important, again, I say this a lot, but I think it's a really important thing. Make sure to distinguish the geometric representation of your algebraic object from your algebraic object. They're not the same thing. There are many different geometric interpretations of an algebraic object, so don't conflate them. Okay, so this is all old news. Y'all know all that from Calc 1. So what I want to do now is kind of rip off that idea in a multivariable context. So we're going to consider now a function from R2 to R1. Suppose f R2 to R1, right? And suppose f is a function of say x and y. How would I mimic this function near a certain point? And I claim that this function here does it. Now, I'm not going to so much derive that as I'm going to justify it after the fact. Okay, but this function, I claim that at the point a comma b in the domain, keep in mind, two inputs, right? R2, two inputs, x comma y. A point in R2 would be characterized by two values, a and b. At a point a comma b, I claim that this L function has the same value that f does. at A comma B. And you can justify it the same way that we would have up here. I mean, how do I justify that at A, F, and L have the same value? Well, take A, plug it in, plug in x equals A, right? That's how you compute L of A. L of A. L of A is what you get when you, everywhere you see x, you put A. There's the only x. You put A in there, and I get 0 over here, and I have L of A equals F of A, as desired. Okay? And we're going to do the same thing down here. What is L of A comma B? Well, we're going to take x equals A and plug that in. Right? We're going to take y equals B. We're going to plug that in. And conveniently, 0, 0, all this junk over here disappears in a puff of smoke, and I'm left with L of A comma B is equal to F of A comma B. So this construction that I've made here has the same value as F at the point A comma B. And by a similar calculation, I claim it has the same derivatives. Now let's be careful with that next part. How do I, I'll show you, how I know this has the same x partial. Let me compute the partial of L with respect to x, and then we'll plug in A comma B. Partial of L with respect to x. What's the partial derivative of that term with respect to x? Keep in mind, this is not f of x comma y. This is f of A comma B. A and B are fixed. They don't change. It's constant. Partial derivative 0. Okay, what is the partial derivative now of that term with respect to x? Now, again, very, very careful. What do we have here? And it's tempting to say that that's some sort of derivative function or something, but it isn't. This is not the derivative as a function of x. This is the derivative at the point A comma B. And so again, this says, do some calculation, get some function, and then plug in these constants. So this is actually just some number. This is a constant. It's whatever the number is, it's whatever the partial of f with respect to x is at that specific and fixed point A comma B. So it's constant. So when I'm taking the partial with respect to x of this term, this is constant times x minus a. And what is the partial with respect to x? Partial with respect to x. Taking the x partial of constant times x. Any theories? It's that constant. That's right. Absolutely. So we get whatever that constant is, and the constant in this case is partial of f with respect to x, A comma B. Okay. All right. Let's see here. Then likewise over here, what's the deal with that? Well, again, this looks like there's some derivative function of some sort over here, but it's not. There's a function into which I've plugged in constants. So this is a perhaps big and scary looking constant, but it's a constant. And all constants, no matter how big and scary, the derivatives are all 0. Okay, so the partial with respect to x of that is nothing. By the way, what's going on over here? Here we have a function y. What's the partial of, with respect to, what's the partial of y? Well, we're taking the partial with respect to x, for which purpose y is constant. So this whole thing is constant times constant minus constant. It's 0. Okay, so we've taken the derivative, but now let's plug in. So what do I get when I plug into this result? Oh, gosh, I need a little bit more space. when I plug into that expression, at the point A comma B, well, the expression into which I'm plugging certain values is 0 plus a constant plus 0. It's a constant. Nice thing about constants, it doesn't matter what you plug into them, they are constants. Right? And so this is just the thing we have on the right, and I have partial of f with respect to x. I don't need those parentheses. A comma b. And so as hoped, as we were expecting, the partial of L with respect to x is the same as the partial of f with respect to x at this point A comma B. Now I don't know what's happening at other values. Who knows? I'm just talking about just at the point A comma B. At the point A comma B, f and L have the same partials. We saw previously f and L have the same value. Now we see they have the same x partial. And I'm going to leave it as an exercise for you guys. And please do this one. Actually write this down. Make sure you are super comfortable with each little micro step along the way. I want you to argue why is it that L and F have the same y partial at the point A comma B as well. Okay, so this function is the mimic, right? This function at the point A comma B, this is a rip-off of f. It's got the same value as f. It's got the same x partial as f. It's got the same y partial as f. It looks just like f. It's tracking f, impersonating f. And again, geometrically now, thinking of graphs. And so, don't forget graphs mean you're setting these functions equal to a new variable, in this case z. The graphs, at the point sitting above A comma B there, the graph of the linear approximation, it's like the, imagine you were a little teeny tiny little ant at that point and you didn't perceive the curvature of the function, kind of like people 500 years ago, right? You would think, hey, the world's flat, and well, the flat that you would perceive is the tangent plane, right? So this, the graph of the linear approximation, you can't tell the difference on a small scale between the graph of the linear approximation and the graph of the original function, and so sort of tangent plane. Okay. All right. What if you have more than two input variables? Well, we're not going to be able to think of the graph point of view if there's more than two input variables. If you have three input variables, right, and one output variable, that means these graphs are going to be four-dimensional. I can't even pretend to be able to draw that, right? Don't try. It's utter failure. So I can't take the graph point of view, but I can still write down linear approximations. This formula here totally works. Just keep adding in extra terms. So, here's the starting value, if you will. I have this term to make the x partial work out the way I wanted. Right? So this term here is what gives rise to that to check out. And then what you'll find when you do this algebra on your own is that this term here is what makes the y partials work out the way they're supposed to. And you just keep adding more terms, and you end up with this. And so again, don't so much derive this. Don't start with something and then do algebra, and then this is your answer. You don't need to do that. Start with this. I propose that this function here is indistinguishable from f at the point A comma B in terms of value, x1 partial, x2 partial, x3 partial, x4 partial, all the partials, however many variables there are. Can't draw the picture. Oh my gosh, no, right? But in terms of the computations of value and partial derivative, this is a total rip-off of f. It's a mimic of f, and again called the linear approximation. Okay. I want to move on to higher order partials. There's some nice geometric questions that come up here, but first let's make an algebraic observation. Here's a function of x and y. I can take its x partial, and look what I get. A function of x and y. Well, if when you have a function of x and y, you're allowed to take the partial derivative of it, well, this is a function of x and y. Can I take the partial derivative of that? And yeah, sure, totally. Go ahead. It's called the second partial, right? Different notations. Oh, yeah, by the way, an alternative notation for the first partial. Here's our partial with respect to x. We talked about this notation. Sometimes it's very convenient to just write x as a subscript. It's understood in this context that subscript x means take the partial derivative with respect to x. And it can be super convenient. We'll see some examples in a week or two. By the way, notice that this notation, the first notation we talked about, remember that I made the observation, it's kind of a smacks of Leibniz notation, right? Dy dx. Right? This kind of smacks of the Newton notation, the prime notation. And you can't just say f prime. Prime doesn't tell you which variable are you taking the derivative with respect to. So you can't. I mean, prime wouldn't do it, but this subscript of x is kind of in as compact a way as possible, telling you take the derivative. And of course, I have to tell you which variables I have to say x. So it's sort of Newton-like in a way. Okay. All right. So you can take the you can take the x partial of the x partial of your original function. One other way that you might choose to write that, by the way, would be maybe you would write it as partial with respect to x of partial of f with respect to x. And so you can see here we start with f, and then I'm doing an x partial of it, and then I'm doing an x partial of that. Right? So, okay, well, with that in mind, notice that a convenient shorthand is that the numerator kind of sort of looks like that, and this always used to bug me when I was learning this for the first time, but the denominator, it sort of looks like you're... I'm sorry, I didn't realize that wasn't on the screen there. It's on my screen here, but... There we go. It's like there's a partial x, and then there's another partial x. It looks like you're multiplying. Now, the reason that this used to really bug me is we're not multiplying, very importantly, right? This is an operator that's applying to another operator applying to f. But notationally, this is convenient as well, and so let it go. Right? I mean, I used to really obsessed, but there's no reason. Just let it go. It's weird and annoying notation, and so be it. Okay. So take all the partials in a row you want to. You can take third partials if you want. All right. Okay. Now, again, who cares? What does this mean? Why is this at all useful? Is this another, silly little algebraic manipulation with no particular application? No. It turns out there is a lovely way to interpret second-order partials geometrically. I have gotten slightly ahead of myself. I forgot to mention this theorem here. This theorem. And that is that surprisingly often the y partial of the x partial and the x partial of the y partial, let me do that better, the y partial of the x partial, the x partial of the y partial, surprisingly often those are the same. You notice it in this example here. I took first the x partial, then the y partial. First the y partial, then the x partial. And we got the same functions. That's weird. Yeah, what are the odds? It turns out that this is usually true. Now, it is not always true. There is a condition. If everything in sight is continuous. Now, specifically, all we need is the second-order partials to be continuous. But in the case, most cases that we deal with, polynomials, all the derivatives are polynomials, they're all continuous. Fine. Trig functions, where they're defined anyway, which is all we ever care about with trig functions, all their derivatives, again, continuous, right? So there's no real problem most of the time. So most of the time, mixed partials are equal, and you can take them in any order you like. And I'm out of time, unfortunately. So I'll get to the geometric interpretation. You know, what do these second partials look like? How do I think about them on Monday? Y'all have a good weekend. Don't forget to turn in your homework up here at the front. And again, just a quick reminder.